Section 32 is on an introduction to related rates. So this is a super important concept on the AP test. So we're going to spend a couple days doing this. So it says you will often see related rates problems, especially on the AP exam. You'll be given the rate of something that's changing, and you'll be asked to find another rate of change. So maybe the volume is changing at a certain rate, and the rate of the radius is changing. In order to do this, you're going to need to differentiate both sides of the equation implicitly with respect to time. So this is something that we have not done before. We have never taken the derivative with respect to time. We have taken the derivative implicitly, right? So we've had equations that look like y squared equals 3xy, and we've taken the derivative with respect to x. And we've done 2y, and we've tacked on a dy over dx. Does that make sense? Do you guys remember implicit differentiation? But now if we're taking it with respect to time, every time I take the derivative of anything, if I take the derivative of an x term, I need to, so if I would have 3 and then times dx over dt, and then times y, right? So I would have to, every time I take the derivative of any variable, I need to tackle on like its variable over dt. Does it make sense? So like if I have an x, I do dx over dt. If I have a y, I do dy over dt. Okay, because we're not doing everything in terms of x, because we were very lazy and didn't write dx over dx when we were doing implicit differentiation. Okay, but now we're taking it with respect to time. It's a little bit weird. So our steps to solving a related rates problem are very similar to optimization. We draw a picture, we choose variables that make sense, we take derivatives, and then we plug things in, right? So it's going to be very, very similar, but we're not optimizing. We're not finding like a maximum volume or a minimum cost or anything like that. And then I said on number 4, substitute in values for all known quantities and derivatives. We always do this after step number 3. You never want to plug in all the numbers that you know and then take the derivative, because if you plug in all the numbers that you know and take the derivative, you're going to get 0 every single time. Does that make sense? So we have to take the derivative before we plug things in. All right, so here's a basic example. It's not really like a story problem setup, but it will show you how it's related to implicit differentiation. Okay, so in the problem, notice how we have dx over dt equals 5, and it says find dy over dt when x equals 2. This is indicating that we're taking the derivative with respect to time, t. Okay, so as I take the derivative of every single variable, the derivative of y is going to be 1, but it's going to be dy over dt. The derivative of x to the 4th is still 4x cubed, but since it's an x term and we're taking it with respect to t, we tack on a dx over dt. And then we have 3 dx over dt. Okay. And we're going to plug everything in. So we know dx over dt is 5, and we know x is equal to 2. We're finding dy over dt. So dy over dt's are unknown. So we have 4 times 2 cubed times 5 plus 3 times 5. So we get 20 times 8 is 160 plus 15. So our answer is 175. So that's dy over dt. Okay. And in the real life examples, we'll have like, you know, units and so on, so we'll be talking about units. But in this one, we didn't have any units given. Okay, do you guys see how that works? So anytime you take the derivative of anything, you're going to tack on its chain, kind of, right? The derivative of the u. All right. So number 2. So it says a 10-foot ladder leans against the side of a building. If the top of the ladder begins to slide down the wall at a rate of 2 feet per second, how fast is the bottom of the ladder sliding away from the wall? So basically what's happening is the ladder sliding down, you don't have to draw this, and it's looking like this, right? Does that make sense? So like the top of the ladder is going down, so the total height of the ladder is getting smaller, but the distance from the wall to the end of the ladder is getting bigger. Does that make sense? Okay, so that's what's happening. So I'm going to call these units x and y. And I usually do that when I have some kind of vertical component and horizontal component, x and y. And we'll call this one z. Okay, do you guys see that z is constant? It's always 10. Okay, we're going to talk a lot about that throughout the next couple days. So I'll mention it in just a second, but it's constant. It's always going to be 10. Okay, but I want to write some kind of equation that relates x, y, and z to each other. Yeah?
X squared plus y squared equals 100.
X squared plus y squared equals z squared. Exactly. We're using the Pythagorean theorem, something you're very familiar with. So as long as you can come up with some equation that relates your quantities, you're good. So once we have that, we can now take the derivative. Okay? Let's write all the different things we know before we take the derivative. Do you know how quickly y is changing? Are we gaining or losing? We're losing, and we're losing 2 feet every single second, right? So for y, I'm going to write dy over dt equals -2. I'm losing 2 feet every second. What about dx over dt? Do we know that one? No, that's what we're finding. How fast is the bottom of the ladder sliding away? What about dz over dt? Am I gaining or losing every single second? I'm not gaining or losing anything, right? That's 0. That's because it's a constant. So basically, when you have constants, you could have plugged in. Do you guys know how Jack just said, oh, it's x squared plus y squared equals 10 squared equals 100. When you take the derivative of it anyway, it becomes 0, right? So if you have a constant, you can actually plug it in, and we'll talk a lot about that. But these other values are not constant. Y is changing, x is changing. We can't plug anything into them. Okay, so we're going to not plug things in yet. Okay, so let's go ahead and take the derivative. So I have I have 2x dx over dt plus 2y dy over dt equals 2z dz over dt. And we can actually divide everything by 2, just to make our numbers a little bit smaller as we're plugging in. That will always happen on the Pythagorean theorem ones. All right, and it says, how fast is the bottom of the ladder sliding away from the wall when the ladder is 8 feet off the ground? So we're saying when y equals 8, we're finding dx over dt. So y we know is 8. If we know y is 8 and we know this is 10, z is 10, can you guys find x? It is 6. Do you guys see it's a 3, 4, 5 right triangle, 6, 8, 10? If you didn't know that, you could do 8 squared plus x squared equals 10 squared, and you would get x equals 6. So we're going to plug in. So x is 6. Dx over dt is what we're trying to find. Y is 8. Dy over dt is -2. Make sure you have that correct sign. You're losing 2 feet every second. Z is 10, but dz over dt was 0 because it was a constant. So we get 6 dx over dt minus 16 equals 0. So I'm going to add the 16 over, so equals 16. So dx over dt equals 16 over 6, which is 8 over 3, which you could write as 2.6 repeating, or 2.667. Okay, and then what are our units? Because you're losing 2 feet every second in the vertical direction. All right, so what are our units? What was x in terms of? Feet. What was time in terms of? Seconds, right. So it's 2.667 feet per second. Okay, so basically you look at your dx and you look at your dt. It's just like a slope, like it's a rate, right? So your x is in terms of feet and t is in terms of seconds. So that's what you're going to look at, x over t. Does that make sense? So that's how you get your units. All right, let's try the next one. So it says, suppose a forest fire spreads in a circle with radius changing at a rate of 5 feet per minute. When the radius reaches 200 feet, what is the rate? At what rate is the area of the burning region increasing? Okay, so we have a circle. And it's getting bigger, so this R is changing. So you don't have to draw this, but basically it's spreading out like this, right? And R is getting bigger and bigger and bigger. So we're saying when R equals 200, we need to find dA over dt. Okay, so how do I represent the area of this region? Yeah, it's a circle, right? Pi r squared. So I take the derivative, so I get 2 times pi r dr over dt. I don't know why I wrote it like that. 2 pi r dr over dt. You guys see how I took the derivative?
It's just because that's the variable.
Right. Whenever you take the derivative of any variable, you need something over time. Yeah. Unless you had t, right, then it would be dt over dt, which is just 1. So since we don't have t in our problem. All right, so dA over dt is what we're trying to find. We're saying when r reaches 200 feet, do you guys see why we couldn't plug it in here at the beginning? Because then if I plugged it in and then I took the derivative, I would always get 0. That doesn't make sense. All right, so I have 200. What our dr over dt is 5 feet per minute. So maybe I should write that over here so you guys can see that was one of the things we were given. So we get 1,000 times 2 pi, so 2,000 pi. Oops, one more 0. Isn't it 2,000?
Well, you need the measurement.
I know, I'm not done yet. All right, so your area is what? Yeah, it's in feet, but it would be squared, right? So feet squared for area. And then our time is in minutes, so feet squared per minute. Okay, and you can find what that is as a decimal too. Sometimes it makes more sense seeing it as a decimal when these are like story problems. It doesn't matter. Okay. All right, so let's do one that's similar. So we still have a circle. But it says an oil tanker has an accident on a bridge and it spills out at a rate of 20 cubic feet per minute. 20 cubic feet per minute. Is it really like an area? When you have cubic feet? Volume, right? So if you want to write yourself a note, that is dV over dt. Okay, Mr. Crowley always says units are the key to life. I agree. With related rates, if you guys can recognize units, it helps you know, oh wait, this is a volume equation. I need a volume formula, okay? So suppose that the oil spreads out onto the water in a circle, but it has a thickness of 1/10 of an inch. In other words, 1 over 120 of a foot. Determine the rate at which the radius of the spill is increasing when the radius equals 500 feet. Okay, so we have a circle, but there's some kind of thickness to it. So it's really kind of a cylinder, right? But that thickness is a fixed 1/10 of an inch, or you could say 1 over 120 of a foot. Is R a fixed number? No, R is spreading out, right? It's getting bigger and bigger and bigger. So R is what we're trying to find. dr over dt, I guess, is what we're trying to find. And we're finding it when the radius equals 500. Okay, so the radius isn't always 500. It's spreading out, spreading out, spreading out, and it's creating this big volume, this increasing volume. Okay, so how do we do this? The volume of a cylinder, right? What is the volume of a cylinder? Pi r squared h, good. Yes, you do have to know these. So pi r squared h. They will occasionally give you formulas, not all the time. All right, so we do have a constant thing in this problem. Do you guys recognize which one's constant? Mm-hmm. Okay, so we could plug it in. So we're allowed to plug in 1 over 120, but I'm going to leave it right now. So I'm going to take the derivative and show you what happens when you take the derivative and why you can plug that in at this point. Okay, so if I take the derivative of this, I actually would need to do the product rule. So I have dV over dt equals pi r squared times dH over dt, right, the derivative of h, plus the derivative of pi r squared is going to be 2 pi r dr over dt, and then times h. But since h was constant, that means dH over dt is equal to 0. It's not changing at all. That thickness is the same throughout. Now, if you have a massive amount of oil leaking, basically the thickness will change. But usually oil kind of like sits on the top of water, right? So the thickness usually is kind of the same. But yeah, if you have a ton of oil and you all of a sudden dump it into water, then yeah, it's going to mix in. You guys have probably done things with like oil and water before, right? You mix them together? No. When you're baking or anything? No. All right, never mind. All right, so anyway, so dH over dt goes to 0. So basically this whole first part of the equation is gone. That's why it doesn't matter that you plugged in the constant, because if I had done pi r squared times 1 over 120, and then I took the derivative, the 1 over 120 and pi were numbers, and then I have 2r dr over dt. That ends up being the same thing that you were getting here, 2 pi r. H was 1 over 120 dr over dt. It ends up being the second part of the equation anyway. Do you guys see? That's why we're allowed to plug in constants. Only constants, though. So I always go to like AP conferences for calculus. And one year I went to one at Butler, and there was a teacher there that was like the worst for students. I could already tell because she was like, "Oh, I never let my students ever plug in constants before we take the derivative." And I was like, "Well, I feel like that's making them do a whole bunch of work that's really not necessary." And she was like, "Oh, well, I mean, it just takes like a couple seconds longer and blah blah blah." But there's problems that are called trapezoidal trough problems, which have a trapezoid. We'll do these. You'll be excited. And there's a length, and then there's 1/2 h b1 plus b2 for the front times the length. You have 4 variables. Can you imagine taking the derivative without plugging things in for constants? It would be terrible. So, I don't know. I kind of got in an argument with her. I was just like, that seems completely unnecessary. You should teach them why you can plug in constants. All right, so dV over dt. Anyway. So dV over dt, do we know that? Yes. Yeah, it's 20 cubic feet per minute. We're gaining 20 cubic feet every single minute, so it's positive. And we have 2 pi. We're allowed to plug in r now because we've already taken the derivative, so r is 500 at this point in time. dr over dt is what we're trying to find, and h is that 1 over 120. Why do you think I'm using 1 over 120 instead of 1 over 10? Yeah, everything else was in feet, right? So we want to keep everything consistent. So sometimes I'm not going to give you that little clue. I'm going to have different units, so be careful. All right, so I'm going to have 1,000 pi over 120, 1,000, dr over dt equals 20. So I'm going to multiply the 120 over. So 20 times 120. Then I'm going to divide by 1,000. So when I do that, I get 12 over 5, but I still have a pi on the other side. So when I divide over, I'm going to have 12 over 5, and the pi goes on the bottom. Be very careful with that. Okay, a lot of people will put the pi on top, or when they put it into their calculator to find the decimal, they forget to put parentheses around the denominator. That is one of the biggest mistakes people will make in related rates. So they come so close, and then they forget that. So if you're actually finding this answer as a decimal, your answer is to go ahead and check with your calculator. Make sure you do it correctly. It should be 0.764 feet per minute. Okay, so make sure you put parentheses around the bottom. If you guys have the fancy type on your calculator, you'll probably be fine where it shows you the denominator. For those of you that don't have the fancy type, you need parentheses. Do not forget. All right, next up, number 5. A snowball. Oh, it seems appropriate. We just had our first snow. Sadly. If a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10. Okay, so we have a lot of things going on here. Okay, so maybe sometimes it helps if you like write the things we know. So we know that ds over dt, the surface area is changing, and we're losing 1 square centimeter per minute. So make sure you put a -1. We're losing 1 square centimeter per minute. And then we want, when the diameter equals 10, we want to find dd over dt, the rate at which the diameter is decreasing. All right, so our surface area equation, this is a tough one. You guys know the surface area of a sphere? Ah, close. The volume of a sphere is 4/3 pi r cubed. I agree with that. No. It is actually the derivative of the volume. If you take the volume and you take the derivative, what do you get? 4 pi r squared. That happens a lot. It's often the derivative of the other one. So yes, we get 4 pi r squared. So I'll try to give you guys like a list of things that you should know. Like that's one I think that you should know. All right, so the problem is we're asking when d equals 10, find dd over dt. Okay, do you guys see how that's a problem? Okay, we don't have any d's in our problem. Okay, but we do know that d is equal to 2 times r. In other words, d over 2 is equal to r. So what we can do is, before we start our problem, if we recognize that we have everything in terms of d, we replace. So we say, well, r is the same as d over 2 squared. And then I tutor a lot of people, and they try to take the derivative right now. Don't take the derivative right now. What do you do first before you take the derivative? Simplify, right? Don't you want to simplify this equation so it's easier to take the derivative of? Right, so we get s equals 4 pi times d squared over 4. So these 4's reduce out. So we get pi d squared. Much easier to take the derivative. So our derivative is going to be ds over dt equals, if we have pi d squared and we take the derivative, we get 2 pi d times dd over dt. 10 crystal. And now we plug things in. So we say, oh, ds over dt, we're losing 1 square centimeter per minute. At that instant in time, d is 10. We're finding dd over dt. So dd over dt ends up equaling -1 divided by 20 pi. Units? What do we think for diameter? Is it squared? Centimeters squared? No. Just regular centimeters per minute, right? That's our answer. So you can find a decimal answer as well. All right, so this is not really like super important in this problem, but I'm going to show you something. Okay? Let's say that you are doing this problem and you're in a hurry, you're doing the AP test, and you realize, oh my gosh, I forgot to change it in the beginning. So you took your equation, and you took the derivative of 4 pi r squared, and you said, oh, ds over dt is going to be 4 pi times 2, so 8 pi r dr over dt. So you did that instead. Okay, it's not a big deal in this one, but if you have a whole bunch of variables and it's a really complicated derivative, it is a big deal. Jacob, pay attention. So if you see that you have taken the derivative and you have the wrong variables, so you can't plug anything in because you're like, wait, d is equal to 10, find dd over dt. Okay, what you can do is you can come up with any secondary equation that relates to the variables you need. So the variables we want, we have r and we want to change it to d, right? So we say, oh, well, 2 times r is equal to the diameter. And then take the derivative of that one. So the derivative of 2r equals d gives you 2 dr over dt equals dd over dt. Okay, what we just did is we related the two rates. This is why this is called related rates. Okay, does this make sense? So then in your problem, you could say, oh, well, I have 8 pi, and then r is really d over 2, and then dr over dt is really 1/2 of dd over dt. And it saves your problem. Does that make sense? So it's not a huge deal in this one. It'd be very easy just to erase and go back through and do it correctly. But if you realize after you took a massive derivative, one that involves like product rule or something, you're like, oh my gosh, I have everything in terms of r and it really needs to be in terms of h. Right? This is something that will save you. So just know that. So if you get stuck in the middle, you can always save it. All right, number 6. So at noon, ship A is 100 kilometers west of ship B. Ship A is sailing south at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? All right, so A is 100 kilometers west of B. A is sailing south at 35 kilometers per hour, so that means dA over dt is 35. We're gaining 35 kilometers every hour. And B is sailing north at 25 kilometers per hour. So dB over dt is 25. So how fast is the distance between the two ships changing at 4 p.m.? So what we're trying to find is this line right here. How fast that line is getting bigger at 4 o'clock. Okay, this is a complicated question. Okay, in order to make it a little bit easier for us, instead of using the 2 triangles, right? See how you have 2 right triangles and you can come up with an equation using the 2? We're going to make it into 1 right triangle. Okay, so what we're going to do is this distance is always 100, right there. This distance is changing. Do you guys see the right triangle? So this whole length, the y, we'll call it y. How much am I gaining? Like how much is y changing every single hour?
60.
It's 60, right? Do you guys see it? dy over dt ends up being the 25 plus the 35. It ends up being 60 kilometers per hour. Do you guys get it? Because one of them is going north at 25 kilometers per hour, and one of them is going south at 35 kilometers per hour. So their total distance is changing by 60 kilometers per hour in the north-south direction. Now the east-west direction is still just 100. And then this distance is the one that we want to find, z. So I'm going to set it up with my x, y, and z again. So I'm going to have x squared plus y squared equals z squared. Right? Is there anything that I can actually plug in? X, sure, if you want to. So we can plug in 100 squared there. All of the rest of them are changing, right? Y is changing, z is changing. Okay, we take the derivative. So this becomes 0 plus 2y dy over dt equals 2z dz over dt. And you can divide by 2 if you want. Clear out those 2's. Kind of a tricky question. We need to know what y is. I mean, do you know? I have a feeling you know. You looked up like, that's very easy. Okay, we left at noon. Their distance between them is changing 60 kilometers every hour. It's 240. Do you guys see it? Exactly. So left at noon. So after 4 hours, the vertical distance equals 240, right? Because it's 4 times 60, which is 240. So that's our y. I don't know what that looks like, a weird arrow. All right, so y is 240. So I have 240. dy over dt is the thing that we said was 60. Z, do we know it? We have 100 here. We have 240 here. Can we find it? It's not 1,000. Okay, well, what do we get? You guys know your special right triangles. You get it right away. It is 260. Do you guys know what special right triangle that's related to? 5, 12, 13. Yeah, 5, 12, 13. All right, so I get 260 dz over dt. You can tell you've been trained by Mr. T with your, yeah, he loves Pythagorean triples. A little obsessed. All right, so we divide it out. So dz over dt equals 55.385 kilometers per hour. Okay, that's our answer. Okay. So next one, so it says, in some problems we're given the rate of change of one variable but not others. We sometimes have to use similar shapes to help solve the problem. Okay, this is a very, very common one, very common problem. I will always put this on the test. I always put an inverted cone. Just know it's going to be there. So an inverted conical tank, so in other words, a cone with its vertex facing down, is leaking at a rate of 6 cubic inches per minute. So what is that? What unit is that?
dV over dt equals
Yeah,
-6.
not unit. That's not what I'm looking. What variable, I guess. Yeah, dV over dt. It's not just 6, but it is -6. We're losing 6 cubic inches every minute. It's leaking out. Okay, so these problems are super important in real life. I know they don't seem like they're important. It's hard for you guys to like see how they're related. But anything that involves a funnel uses this problem. Okay, so on the bottom of grain silos, you drive trucks underneath them. I can show you a picture. And it's a little funnel, like it's funneling into the truck, right? Or like water towers, right? We have funnels involved with them. So it's a super important problem. All right. So it says the height of a cone is 12 inches. So the height of the whole thing is 12. And the radius along the top is 15. I still didn't draw it very well. Needs to be like much fatter. So find the rate of change of the radius when the height of the water is 8 inches. Okay, so this is just the structure. The structure is 12 inches and 15 inches in diameter. But the water on the inside, we don't know what the height and the radius of that is. Okay, so as this water is dripping out, so as we're losing 6 inches cubed per minute, right, the radius and the height of the water is also changing. Do you guys see the radius is getting smaller, the height is getting smaller? You understand it? So what happens every single time in these problems is you can set up similar triangles. Do you guys see what I'm talking about? You have 15 here, you have 12 here, you have some kind of radius and some kind of height. So we have similar triangles. So we can set up a proportion that says, well, 15 is the radius of the whole tank divided by r, the radius of the water, is in the same proportion as 12 over h. So we always set up some kind of equation. This was like a secondary equation that's going to help us. All right, so let's start the problem. So we want to find the rate of change of the radius when the height of the water is 8 inches. Okay, we're using the volume of a cone. The volume of a cone, it's similar to a cylinder.
1/3.
Yeah, it's 1/3 pi r squared h. I know, he's good. He's got this down. All right, it's 1/3 the area of the base times the height. All right, and you can take the derivative at this point, but the derivative is going to be messy. Do you guys all see this? When you take the derivative, is it going to be a little bit gross? It's going to be a little bit gross because we're going to have the product rule. Right? It's going to be very long. You can do it. It's fine. All right, if you don't want to do that, you can change things around using your similar triangles. You can get things all in terms of r or all in terms of h. Now, this problem doesn't really help you out much because it says, find the rate of change of the radius when the height is 8 inches. So it's like, crap, which one do I do? Do I do r or do I do h? It doesn't matter. You can do either one. But every single time you have these problems, you don't have to do the product rule. Because you can very quickly multiply here and say, well, 15h is equal to 12r, and solve for one of them. So since I'm finding the rate of change of the radius, I'll go ahead and solve. So I can change everything to radius. So I'll solve for h. So h is going to be 12 over 15r, which reduces, divide by 3, to 4 over 5r. So in our original problem, we can simplify before taking the derivative. We can say, well, h is really in the proportion of 4 over 5r, right? No matter where the water is, it's always in that same ratio. Do I take the derivative now? No, please simplify. Please, for the love of God, simplify before you take the derivative because it's terrible if you don't. So you get 4 over 15 pi r cubed. Now we take the derivative. So dv over dt equals, I'm going to have that 4 over 15 pi out front because that's just a constant. And then I take the derivative of r cubed, it's 3r squared dr over dt. Right? If I did the rest of the product rule, it would be 0. There's nothing left. We continue to simplify. So like the 3 and the 15 make 5 on the bottom. So I have 4 over 5 pi. I have r squared, and then I have dr over dt. dr over dt is what I'm trying to find. dv over dt, I know, it's -6. So I have almost everything, but I don't have r. So all is not lost. Right, we can get it. Any suggestions on how to find r?
You use proportions.
Use proportions, what do you know already?
The height of the water is 8 inches.
Yeah, we know at that point in time that we're trying to find, the height is 8. So if h is 8, then r is equal to, you can plug in anywhere.
10.
Yeah, so you'd have 8 equals 12 over, or 4/5 r. So multiply, you get 40, divide by 4, 10, exactly. So we're going to plug in 10. We just solve it out. That's it. So I tend to try to do like one thing at a time. Like I would multiply the 5 over and get negative 30. And then I have 400 pi. And then I would divide by the 400 pi. So I have negative 30 over 400 pi. Just make sure that the pi goes in the correct location. A lot of people will put it in the numerator. So if I reduce it down, I get negative 3 over 40 pi. Or you could multiply the pi in. Just make sure you put it in the denominator. And you get negative 0.024. What are my units? Inches for radius per minute. Yeah, inches per minute. That's that. Okay, does that make sense? So remember, it would have worked out fine if you had left the r and h in there. You could have taken the derivative with r and h. You could have used that secondary equation to solve for r and h. You could also get the rates related, right? At this point right here, you know, 15 dr over dt is equal to 12 dh over dt equals 12 dr over dt. You could always do that. Like you can always save yourself if you do something that takes a bit longer. Okay, to use those related rates to help you. Oh, I do want to mention one last thing too. On the AP test, they're always going to look for a final sentence. So on ones like number 5, so it said, find the rate at which the diameter decreases. You have to be very, very careful. You cannot do double negatives in math. Does this make sense? So you can't say it decreases at a rate of negative 1 over 20 pi centimeters per minute. Do you understand what I'm saying? So you would have to say it decreases, guys, are you paying attention? You would have to say it decreases at a rate of 1 over 20 pi centimeters per minute. Or you could say the rate of change is negative, blah, 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 blah. Does that make sense? Don't say decreases and then negative. So always kind of write that final sentence at the end, too. So you might want to kind of get in that habit with your homework as well. All right.